So continuing to talk about pressure, talking a little bit about what pressure is. Okay. So we've been talking about all these molecules. Now they're contained within a certain container like this. For example, um, we have random molecules moving at different points. They have a collision with velocity. They some velocity this way, some velocity this way. Doesn't really matter. Just for the sake of illustration purposes here. Okay. Every single molecule will combine with the container at some point, or crash into it, something like this. So at this point, this is the container wall like this. Or whatever it is. And this is the molecule. It exerts a force on this. That should be straight down, by the way. It exerts a force on the wall, and of course the wall exerts on that. But for the sake of this argument, we just only need to consider the force that's exerting on the wall. Okay. More often than not, it is a lot easier. Okay. Who wants to measure the forces of all of these molecules exerting on it? Relatively speaking, it's actually quite small. But I want to consider, for example, because each molecule is putting force on it, and it's occurring over a certain area, we don't really want to use the force to measure this concept or idea. So, similarly to what we talked about a few chapters ago, when we were talking about solids, we talked about a quantity called stress, right? And the stress quantity is the ratio of force to its unit, to its surface area. Okay. Where this is force and this is surface area. Okay. And the difference was that stress was vectored because we could orient stress around any particular point. We can orient the stress or we can orient the area. We cannot do that in this case. This is impossible, right? Because the container or whatever it is in has a fixed position. So, because the position is fixed, we don't have the vectorial nature of this particular quantity, which has the same exact definition as the previous quantity stress we talked about. This is called pressure. Okay. This is called pressure. Okay, we'll use capital P for pressure. Okay. Pressure is defined as the ratio of force to units to its area. Okay. Something like this. Alright. It's a different quantity, but the difference of area is fixed. And this is not vectored at all. So we don't have to worry about all kinds of other issues at play. We can just consider the fact that each molecule exerts a pressure on the container, which is in a fixed position. Okay. Now, of course, you'll recall that I can manipulate this equation and solve it accordingly. Okay. This is pressure. I will give you a word definition here. So the definition of pressure is the ratio of force to surface area of a particular quantity. So Oops, this is an ugly box, but it'll have to do. Okay. Hold on. Okay. And of course, the ratio of this pressure is equal to force divided by area, like that. Now, recall. And of course, as with any situation, we can create a situation where we add all, because the molecules themselves we don't want to consider all of the forces, we want to add them together. We want to consider their average force, or the sum of the forces, like this. So we of course can write this equation as pressure is the sum of all forces over the total surface area. When you can manipulate it so that sum of forces is equal to pressure times area. Okay? Now, that we've done this, we can talk about the units of pressure. Of course, we recall force is measured in newtons, and of course, area is measured in meters squared. And just like, just like the stress quantity is measured in pascals, pressure is also measured in pascals, which is the ratio of Newton per meter. Newton per meter squared. I'm sure you've all heard the joke when Einstein, Pascal, and Newton were playing hide and go seek, and Newton was hiding in a box, or like a square. All right, and so Einstein goes to find Newton, and he says, "Oh, I have found you." And then Newton goes, "No, you found me over square meter. This is Pascal." Something like that. But anyway, lame physics joke. Now, we'll speak to this like this. Alright? Right, so now that we've gotten the lame physics joke out of the way, we can work with this quantity. Pascal is very small. 1 Pascal is extremely, it's a small unit. So sometimes you'll see it measured in kilopascals, and sometimes there's other units too, but I'm strict physicist, so I expect you to put everything in pascals. So deal with it, okay? Alright, let's erase this. And let's talk about the quantity of the sum of forces a little bit here. Okay? Recall that the sum of all forces here is equal to F1 plus F2 plus F3 plus all the way Fn. Right? We remember all this. This is definition of the sum of forces, or the net force. Okay. I can, using our pressure definition, rewrite this and write this as P1 A. Alright, and the area is in a fixed position, so this is constant, so it factors out. And then factors out P1 plus P2 plus P3 plus all the way to P sub n. And this is A. And this will be called the sum of all pressures. And this is the sum of all forces here. Okay? And so this is another expression that we can say the net force is equal to area times the sum of all pressures. Something like this, right? Add all the pressures together and add all the forces together. We can certainly find the sum of forces. Now, that said, for example, how we do this in a situation, how many of we recall our free body diagram? So let's kind of clear this out. Actually, I will continue working with this here. So let's say, for example, we have a situation like this. We have a wall like this, and then we have a situation here. We have the gas molecule here that's exerting pressure, exerts a force this way, and there's an outside force this way, F2, we'll call it F1. Alright? And so it is important to know in this situation that there's also a situation where you can have a pressure difference, and this causes the net force as well. Alright? So it's very important to keep that in your heads and keep that in mind. Alright, so the way we could write this is, of course, right, this is the same situation when we have like a difference in forces, something like this. F2, F1, sum of forces is equal to F2 minus F1 is equal to P2A minus P1A equals A times the change in pressure. Your book uses a lowercase p, but I will use capital P as to not confuse you with momentum. We use script P for power, so that's going to be something like that. So when we have on two different sides of surface a difference in the pressure, then we'll have net force, or sum of forces in that situation. This is another key equation for you to memorize. Okay. Now, like for example, the situation in like with your jars when you try to open them, okay, you have a difference in pressure. You have the difference in pressure. You have to exert force from the outside, right? The jar doesn't open simply to just you grabbing it and doing that like that. You have to actually put a force on it and twist and turn it to make this happen. So that's why your jar opens, because there's a lower pressure on the inside than there is on the outside. So you have to work like that. Okay? Now, with that we know that. Okay, now that we know that, we can kind of work with the situation. Okay. And as you know, in a vacuum, there's no pressure at all. In pure vacuum, there's no pressure. So this is ideal situation in abstraction, but um, kind of like in vacuum. So when we're traveling at speed of light, we don't really have pressure to consider. Okay. Now, your textbook measures. This is something very important to consider here. We have a couple more points to mention, and we'll be done with this portion of the lecture. Firstly, here, your book talks about measurements of pressure. I want everything done in pascals. I want all pressure units done in pascals. All of them done in pascals. So we'll be doing that. Don't if you have it in atmospheres, change it. Okay. The next point. So we have one. All right. We'll always measure it in pascals. We'll always do our pressure in pascals in the SI unit. Okay. And if you see it in PSI, right, pounds per square inch is the same as 100 pascals. Okay. Please do all pressures in pascals. I would prefer it this way, and it's better this way. Okay. And another point to consider is that when you have pressure on like a gauge or a scale, for example, like when you're reading the scale on your tire, this is different than the pressure that's on the outside. It actually differs by a degree of atmosphere. So your pressure, so the pressure that you read on your scale or your gauge, we call it PG for the gauge pressure, not PG for the moving, is the true pressure on the or the absolute pressure minus 1 atmosphere or minus 101, 300 PA. It's written as 1 atmosphere in your textbook, so I'll write it down. But sometimes you'll have situations where you're reading it off of a scale, and you'll have to add 101, 300 pascals to change the pressure. You have to sometimes add it to do it. Okay. So be very conscious of that. So be very conscious of that when you're working with it. The scale differs by a degree of 101, 300. Okay. Now, let's do example working with pressure. Okay. Let's do an example working with pressure, and we'll conclude this section. We'll work with the ideal gas law next. Okay. Okay, we have an example here. A sphere of radius 5 meters. This has, let's see, let's say we have mass of 300 kilograms, and $500 newtons, and I want find the change in pressure of the sphere. Okay, simple enough. So we have given to us R is equal to 5. We're given mass of 300 kilograms. And given a force of 500 Newton. And we want to find the change in pressure. Okay. So in this situation, right, we have the sphere, which will draw the dot. Okay, and we're looking at it like that. So we have force down like this mg, and another force like this F, like that. Okay, and of course, the sum of forces in the situation will equal either F minus mg. It doesn't really matter. By the way, mg will actually in this situation be bigger. I can just tell you. So it will be mg will equal mg minus F, and that is our sum of forces in the situation. Okay? And of course, to get the area, and of course to get the pressure from this, we know that area, surface area of a sphere, is 4 pi r squared. So the change in pressure is equal to mg minus F over 4 pi r squared. Then that's it symbolically. And so we solve it. 300, 9.81 minus 500 over 4 pi times 25. Okay. So 300 times 9.81 minus 500 divided by 100 pi we'll get a 7. So our change in pressure is very small, is 7.78. The units for this are pascals. So pascal is a very small unit of pressure, and we'll be working with that throughout, and I'll teach you a little bit more about it later. So we'll be working with this concept of pressure, and you'll recall a little bit of it from chapter 11, where we talked about the pressure volume diagrams, a little bit, not much, but a little bit of it. And so we'll be working now with pressure to get us to understand work for the gas. I'm going to talk about that in a bit. Okay.